So in the last lecture we discussed about a vector space definition over vector addition. Now we'll see about some of the properties or axioms related to scalar multiplication. So we'll define certain properties. So the first property on the scalar multiplication with n1 is for all scalars alpha that is belonging to a field f, and for vectors like suppose x is a vector that is belonging to a certain vector space V, we say the multiplication of the scalar with a vector is bound to belong to a vector space V. If this property is satisfied, this is also one of the key criteria in order to define that your required vector belongs to that particular vector space. So required vector is defined as a vector space. So this property normally we say it as closure property. Closure property. Closure property for scalar multiplication. Now, the second, for any two scalars, that is alpha beta for this case, that is belonging to a certain field f, and for every vector, let's say x belonging to vector space V, we can say that multiplication of both scalar times the vector multiplication is nothing but equals to scalar multiplication of alpha times beta times the vector multiplication. Similarly, for the third point, we can say that for every alpha belonging to certain field f and all vectors xy belonging to V, we can say that alpha, the multiplication of scalar with an addition of two vectors, is nothing but alpha times the vector x plus alpha times vector y. I believe in some textbook it is called as distributive property. However, I am not sure, but we'll see. Distributive property. So point number 4, for every alpha beta belonging to field f and for every vector x belonging to set V, the addition of two scalar and multiplied with a vector will nothing but alpha times x plus beta times x vector. And the fifth property is that one times the vector x bar will give me the vector itself for every x bar belonging to the set V. Okay, there is a slight how will I say, from the starting I might have been considered this as a vector space, but this is not how we define it. We say a vector belonging to this particular set like, okay, let me rephrase it for the first time. For the point 1, we say that for every scalar that is belonging to a field, that is belonging to a field, and for vector belonging to a particular set V, it is supposed, if it satisfies this property alpha times x bar, then the resultant should also belonging to that particular set V. And if it happens, like if, then we can consider that particular vector as a part of a vector space. It satisfies one of the key criteria to hold, saying that we can consider it as a vector space. So this is, I am speaking for one property. Similarly, simultaneously, it has to satisfy all 10 properties. It has to satisfy for the second one like that. For any two distinct scalar that is defined over field F and vector X is belonging to set V, we say that the multiplication of two distinct scalars times this vector is it is represented as alpha times beta times x bar. So here, as we can we have already discussed in addition, while discussing about vector addition, examples of the vector addition for vector space. Here also it follows a similar kind of structure. That is the associative rule, I believe. The order of multiplication is irrelevant for this kind of operation, and if it is satisfying this rule, then it again checks one of the key criteria, considering that this vector x might satisfy to be a vector space. Like if yes, this vector, then we can slowly might consider for saying that this vector belongs to a vector space V. So like this, we have to check for every other condition. And if it satisfies all 10, then only we will be able to say that this any vector that has been defined over this particular set is a vector space.